Flying to the moon is already one of humanity's toughest challenges. But SpaceX is now tackling something even harder: refueling Starship in orbit. In a rare statement, Gwynne Shotwell revealed that SpaceX's approach to this critical step isn't what most experts expect. Behind the scenes, the company is quietly developing a smarter, safer refueling strategy that could redefine lunar missions. Let's dive right in. When Gwynne Shotwell walked onto the stage at World Space Business Week, the room went silent. She wasn't there to deliver rehearsed optimism. She was there to confront one of the hardest truths in modern rocketry. Refueling Starship in orbit is nearly impossible. And yet her tone wasn't defeated. It was sharp, deliberate, the kind of tone that says we know exactly what we're up against. Because when it comes to reaching the moon sustainably, there's no alternative. If humanity ever wants to build lasting outposts beyond Earth, orbital refueling isn't an option. It's the foundation. Starship's lunar version, known as HLS, or Human Landing System, is designed to take astronauts from lunar orbit to the moon's surface and back. But the real battle starts long before that. To complete the round trip, the HLS needs about 1,200 tons of propellant. Yet, a fully loaded Starship launched from Earth can only carry around 150 tons into orbit. That's a massive gap. For years, analysts believed SpaceX would simply make up the difference with a chain of refueling missions, one launch after another, filling a depot until the HLS was ready to depart. But former NASA Administrator Mike Griffin threw cold water on that idea. His calculations showed a single lunar mission could require 10 to 16 separate tanker launches. Each docking, each transfer, each synchronization adds risk. Even if every individual event is 99% reliable, stacking them together multiplies the odds of failure. And then there's time, the silent enemy. Cryogenic propellants like methane and oxygen slowly boil away in orbit. The longer a depot waits for tankers to arrive, the more fuel is lost. If one flight slips, the mission window can collapse. That's why Shotwell called it nearly impossible. Not because it can't be done, but because the system, as originally designed, was too fragile to trust with human lives. If Apollo reached the moon without orbital refueling, why bother now? Because Apollo's architecture was never scalable. The Saturn V rocket could lift 48 tons into lunar orbit, just enough for a small lander and a few days' worth of science. Each mission was a one-off event. No reuse, no long-term base, no expansion. Starship is built for a different era: sustainability and scale. It's not about visiting the moon. It's about staying there, carrying habitats, rovers, and supplies for months, not days. That kind of mission requires refueling. There's no way around physics. That's why, despite every warning, SpaceX doubled down. And Shotwell's comments revealed something deeper. They're not repeating the same plan. They're redesigning it from the ground up. The in-orbit propellant transfer will be our most critical challenge, as she said, but it's one we're building for right now. That phrase, building for right now, wasn't a slip. It was a hint. What Shotwell hinted at is a major internal shift: SpaceX's orbital depot strategy. Instead of making the lunar lander handle dozens of risky dockings, SpaceX plans to launch a dedicated refueling depot, Starship First, essentially a gas station in low Earth orbit. Once in place, a fleet of tanker Starships will launch sequentially, each delivering liquid methane and liquid oxygen to the depot. Using precision docking systems and cryogenic plumbing lines, fuel will be transferred slowly to avoid vibrations or thermal shock. Once full, the depot acts as a stable, verified fuel source. The HLS Starship then launches, docks once, fills its tanks, and departs for the moon. It's a simple concept on paper, but revolutionary in execution. This new structure cuts down risks dramatically. Fewer dockings, fewer chances for failure, and tighter control over temperature and pressure throughout the system. Behind the scenes, SpaceX has already begun ground testing cryogenic transfer tanks, massive steel prototypes built to simulate microgravity flow conditions. Engineers are experimenting with fluid dynamics, valve behavior, and pressure control under vacuum environments. The results of those tests will determine when, not if, full-scale orbital refueling becomes reality. When Shotwell says something is nearly impossible, she means it in the strictest engineering sense, not emotionally, but mathematically. Cryogenic fluids behave unpredictably in zero gravity. Gas bubbles, ice crystals, or thermal gradients can cause sudden imbalances. Even a small pressure fluctuation can force liquid out of alignment, leading to cavitation or unstable flow. And since Starship relies on two propellants, liquid methane and liquid oxygen, both must stay at precise ratios and temperatures during transfer. That's what makes the operation so complex. But complexity is exactly where SpaceX thrives. They've spent years perfecting autonomous docking with Dragon capsules on the ISS. The same LADAR systems that guided those missions, capable of millimeter accuracy, are now being adapted for Starship's docking ports. The leap isn't as big as it seems. It's not reinventing the wheel, it's scaling it up. While SpaceX engineers refined the depot plan, aerospace analyst Tim Dodd proposed something that caught everyone's attention: a smaller optimized lander called the Stubby Starship. Instead of carrying 1,200 tons of propellant, the Stubby would carry just 400 tons and skip the heavy trans-lunar injection hardware entirely. The idea is simple. Let a separate lunar tug or depot perform the push from Earth orbit to lunar orbit, while the Stubby HLS focuses only on landing and ascent. This single change cuts mission mass, risk, and cost dramatically. Instead of needing 10 to 16 tanker flights, it could require as few as 2 or 3. Because the Stubby is shorter, its center of gravity is lower, making landings safer and more stable. It also burns less fuel and maintains an extra 700 meters per second of delta-V reserve, a critical safety margin for real-time course corrections or terrain avoidance during descent. This design doesn't just simplify operations. It gives astronauts flexibility and safety that the full-scale HLS struggles to match. Now this Stubby fix introduces a new technical challenge: a nose-to-nose docking between the tug and the lander during the translunar injection burn. That docking interface must withstand up to 1,800 tons of thrust while keeping both spacecraft perfectly aligned. It's an engineering hurdle, yes, but one within SpaceX's reach. Their Raptor engines can throttle precisely. Their structural designs already handle higher forces during atmospheric re-entry. It's not easy, but it's not outside the realm of proven capability. In fact, it mirrors SpaceX's design philosophy: break massive problems into smaller, solvable parts. Where others see a moonshot, SpaceX sees a system of checklists. This is what makes Shotwell's statement so powerful. She wasn't warning investors or tempering expectations. She was sending a coded message to the industry. SpaceX isn't guessing anymore. They're testing, validating, and iterating at a speed no traditional aerospace company can match. Each Starship flight, no matter how it ends, produces data that feeds directly into the next design, and the numbers are shifting in their favor. Every improvement in tank insulation, every refinement in cryogenic management, pushes orbital refueling from theory into reality. The transition from nearly impossible to inevitable isn't dramatic. It's incremental. It's one valve redesign, one simulation, one flawless docking at a time. If SpaceX succeeds, the impact extends far beyond NASA's Artemis program. An operational refueling system means reusable deep space transport, not just to the moon, but to Mars and eventually beyond. It means smaller rockets could deliver payloads to orbit and rely on depots to top off before heading deeper into space. A complete shift in how missions are designed and financed. And if the Stubby HLS becomes part of that ecosystem, it could accelerate the timeline for establishing a permanent lunar base by years. Because while the full-scale Starship represents ambition, the Stubby represents adaptation, the bridge between vision and practicality. As of now, Flight 11 looms large. SpaceX is preparing to test new tank configurations, refine plumbing systems, and improve guidance software. Shotwell herself admitted, "Our Starship team needed that last win." And they got it. Each successful test adds credibility. Each failure adds data. Step by step, SpaceX is building not just rockets, but trust, the most valuable fuel in aerospace. Because when you're dealing with missions where a single valve can determine the fate of astronauts, credibility is everything. And that's what makes Shotwell's leadership so distinct. She doesn't promise miracles. She promises progress and delivers. So, was she warning the world when she called lunar refueling nearly impossible? Or was she preparing us for what comes next? Because behind every cautious phrase was a quiet confidence. SpaceX isn't just planning to solve orbital refueling. They're already evolving it. And if the Stubby concept proves successful, it won't just fix a problem. It will redefine the roadmap for human spaceflight entirely. For the first time in history, we might see a sustainable, repeatable path to the moon. Not once a decade, but whenever we choose to go. And this is exactly why Shotwell's statement matters. What many saw as a warning, nearly impossible, was actually a challenge. SpaceX isn't backing down. They're building the foundation for how humanity will refuel, travel, and live beyond Earth. If the Stubby Starship succeeds, it won't just change one mission. It could reshape how every future journey to the moon and Mars is done. What this means is simple. The next great leap in space exploration won't come from one big rocket, but from smarter, reusable systems that work together, efficiently, safely, and sustainably. So what do you think? Could the Stubby design become the key to unlocking long-term human presence on the moon? Share your thoughts in the comments. I'd love to read them. This is Space Hub, where we dive deep into the breakthroughs shaping our journey to the stars. If you found this video valuable, like, comment, subscribe, and turn on notifications so you never miss what's next. The future of space is unfolding, and you'll see it here first.